2 in terms of applications to integral calculus is a familiar topic from Unit 3 where we look at how to apply integral calculus to 1D motion. Okay, the same way as in Unit 3 we applied differential calculus to 1D motion. Okay, so as a brief review, remember that connecting position, velocity, acceleration occurs via differentiation. Specifically that velocity is the derivative of position, okay? And that acceleration is the derivative of velocity and hence the second derivative of position. So what this means as a result is that we go in reverse. That means that velocity is going to be the antiderivative of acceleration, and that position is going to be the antiderivative of velocity. And so it's from this that provides us a key in order to move from acceleration to velocity and position instead of just moving from position to velocity and acceleration. So now with integrals and integration in our tool belt, we can actually move in reverse from acceleration to velocity to position instead of just from position, velocity, and acceleration. So let's take a look at how to do this. So determining equations of motion from acceleration. All right, so let's say instead of being provided a position function and having to determine velocity and acceleration functions, let's say you provide an acceleration function, a of t, and we have to determine the velocity and position functions, okay? So determining a velocity function from an acceleration function can be accomplished by using separation of variables and integration in order to solve for v of t, okay? So let's say we're moving from we have a of t, and we want to determine v of t, and we know some initial information about our velocity. Specifically, we know that at time t equals 0, our velocity is equal to some number v naught, where v naught can be 4, 6, whatever we want to call it, okay? So what we can do is we can set dv over dt equal to a of t, all right, since acceleration is derivative of velocity, and we can separate, which gives us dv equals a dt. Next, what we can do is we can find the antiderivative of both sides using separation of variables and integral calculus. And then lastly, we can use the initial information to solve for c. We can use v naught, or v at t equals 0 equals v naught to solve for a constant of integration, c. And then lastly, after we found our constant of integration c, we're going to solve for our resulting equation for v of t, okay? So once we have v of t, we can also apply the same process to solve for x of t, our position function, where this time, instead of setting dv over dt equal to a of t, we're going to set dx over dt equal to v of t, and then use separation of variables to solve. So the procedure is the same, moving from position to velocity as it is, or excuse me, moving from velocity to position as is from moving to acceleration to velocity. So let's take a look at what this looks like in practice. So example 1, developing kinematic equations for free fall, a familiar topic from AP Physics. So suppose an object is thrown upwards with an initial height of y naught, or excuse me, y at t equals 0 equals y naught, and an initial velocity at t equals 0 of v naught. If the object is subject to a vertical acceleration of negative 9.8, so our acceleration function is just negative 9.8, or negative g for the AP Physics people, we ask what is the equation for the object's velocity v as a function of time t. So what we can do right here, all right, is we start off by setting dv over dt equal to a of t, which means we're going to have dv over dt equals negative 9.8. So we separate this out by multiplying both sides by dt to get dv equals negative 9.8 dt. So now what we do is we integrate both sides and find the antiderivatives. So dv is going to give us just v back, or we can write it as v of t since this is ultimately going to be a function of t, okay? And then the antiderivative of negative 9.8 with respect to t is just going to be negative 9.8t plus c, okay? So now we found our antiderivatives of both sides, so now we're going to use our initial condition in order to solve for c, our constant of integration. So at t equals 0, we're going to have our initial velocity is v naught, so we're going to have v naught equals negative 9.8 times 0 plus c, which gives us v naught equals c, our constant of integration. So as a result, we're going to get that if an object is thrown upwards with an initial height of y naught and initial velocity of v naught, we're going to get that we can predict the object's velocity at any time t by the equation v naught minus 9.8t, which, for those of you on for AP Physics last year, is one of the kinematic equations. Ooh, pretty fascinating stuff. So now what we're going to do is see how we can use separation of variables in order to get our second kinematic equation from AP Physics, okay? So now what we're going to ask is, what is the equation for the object's position, y, as a function of time, t? So now we're going to repeat the same procedure again, except now we're going to set dx over dt equal to our velocity function, and then we're going to separate our variables again by multiplying both sides by dt. So multiplying both sides by dt, we get dx equals our velocity function times dt, which is going to be v naught minus 9.8t, our velocity function times dt. So now we can integrate both sides to find the antiderivatives of both sides, okay? And that's going to give us x of t, our position function, equals v naught of t. V naught is a constant, so the antiderivative of v naught is going to be v naught times t, minus 9.8 t squared divided by t.
Can I please have Charlie Gothier to the front office? Thank you.
So as a result, we're going to have 9.8 times t. The antiderivative of that will be 9.8 times t squared divided by t, plus the constant of integration, which I forgot right here, okay? So as a result, we're going to have v naught t minus 4.9 t squared plus c, where the 4.9 comes from 9.8 divided by 2. So as a result, we now use our initial information in order to solve for a constant of integration. This should be a y right here instead of an x. Y is used to denote the vertical height. X is used to denote horizontal position, okay? So just swap out the x with a y. So as a result, at x at t equals 0, x at t equals 0 is going to be equal to x naught or y naught, whatever you want to call it. And then we plug in t equals 0 on our right-hand side, which is going to give us v naught times 0 minus 4.9 times 0 squared plus c, which gives us that, which leaves us just c on the right-hand side, so x naught is going to be equal to c. So if we replace c with x naught, that gives us our equation of motion. X of t, our position at any time t, is equal to our initial position plus our initial velocity times time minus 4.9 times t squared, which for y'all in AP Physics last year is our one of our main kinematic equations. So we can see that kinematics is nothing more than application of differential and integral calculus. So change in velocity and displacement, okay? So change in velocity. Your change in velocity is going to be represented by a definite integral of your acceleration function from t1 to t2, and then your displacement is going to be represented as a definite integral of your velocity function from t1 to t2. Okay? Displacement is what we call our final change, is what we call our change in position, our delta x. Okay? So change in velocity is given by definite integral of acceleration from t1 to t2, and then displacement, your change in position, is given by your definite integral of velocity from t1 to t2. Okay? So what we can do here is that if we are given a initial velocity or initial position, and we want to figure out a final velocity or a final position, what we can do is we can recall that from when we studied the fundamental theorem of calculus in Unit 4, we can recall that final equals initial plus a change in quantity. So we can have our final velocity equals initial velocity plus our change in velocity, which is going to be represented by this definite integral right here. So final velocity is going to equal initial velocity plus the definite integral of acceleration from t1 to t2.
Ms. Carlson, please dial 7000. Ms. Carlson, please dial 7000.
And likewise, our final position is going to be given by our final position plus equals initial position plus our change in position, which is given by our displacement, the definite integral. So final position will equal initial position plus the definite integral from t1 to t2 of your velocity function. Okay? So that provides us a nice little way that we can make sense of everything that's going on here so far. So the next big thing we have to distinguish is between distance and displacement. Okay? Distance is a positive quantity that describes the length of the path required to reach a point. Usually we'd spend much more time with this if we were in AP Physics, because AP Physics spends a lot more time with physics than AP Calculus does, but here we're going to get the rundown version. So distance is a positive quantity that describes the length of a path required to reach a point. Essentially, whatever path that you travel on, if you take a tape measure and measure the length of that path, that is your distance. Displacement, however, is a quantity that can be positive or negative that describes your change in position of an object from one point to another. It describes essentially how far you end up from your original point, with the displacement being positive or negative, describing if you end up to the right with a positive displacement or to the left, a negative displacement of where you originally started. Okay? So to give you some examples, all right, the green path, if I go from home to school, the green path right here represents my distance if I go on this green path. This red path right here, if I measure the length of this, would give me my distance. But my displacement is going to be represented by the blue arrow because that represents how far I end up from my original position, which is home. Okay? To give you another example, okay? If this person right here walks from point A to point B to point C to point D and then back to point A, their overall displacement is 0 because they end back up where they originally start. Their change in position is 0. However, their distance traveled is going to be 3 plus 5 plus 3 plus 5, which in this case is going to be 16 meters, okay? So distance versus displacement, distance is always going to be a positive quantity that measures the length of a path, whereas displacement measures how far you end up from your original spot at the end of a certain travel, okay? And then distance traveled at point A, it says right here, 0. No, that should say 16 meters, but displacement at point A is 0, okay? So whatever website used this needs to correct that. So distance versus displacement, okay? So please note that distance is independent of direction, while displacement depends on direction, okay? So for example, if I travel 50 meters to the left and 50 meters to the right, my displacement if I travel 50 meters to the left will be negative 50 meters because I end up 50 meters to the left I originally started. Whereas if I travel 50 meters to the right, my displacement will be positive 50 meters. But in each case, the distance that I travel is 50 meters, regardless of which direction I had. So to express this in terms of an integral, distance is the definite integral of your speed function from t1 to t2, where speed, again, is the absolute value of velocity, because speed does not consider direction. So we need to get rid of the positive or negative sign, which means we take the absolute value of our velocity function, and then we take the definite integral of that, okay? So it's going to be a definite integral of the absolute value of your velocity function, okay? Whereas displacement is strictly the definite integral of your velocity function without considering the absolute value of your velocity function, okay? So give us a real clear example of distance versus displacement, okay? Let's suppose that we have a car that's traveling along a straight stretch of road from time t equals 0, time equals 15. According to data collected from its speedometer, its velocity during this followed the trends of the graph below. Okay, for I, we can ask what is the car's change in position during this time? Okay, so the car's change in position right here refers to displacement. So in order to do that, we calculate the definite integral of our velocity function from 0 to 15, which means we're just going to find the area between the time axis and our velocity curve right here. Okay, so that's going to be 1/2. So we have a triangle right here that has a height of 10 and a base of 5, so 1/2 of 5 times 10. And we have another triangle right here that has a base of 5 again, from 5 to 10, but has a height of negative 10, so negative 1/2, 5 times 10. So these two triangles right here are going to cancel out. And then lastly, we have a rectangle that has a base of 5 from 10 to 15 and a height of negative 10. So we're going to have from 5 to 10, or from negative 5, or from, we're going to have minus 5 times 10 gives us negative 50 meters. So negative 50 meters is going to be our displacement. Okay? If the car started at initial position of x naught equals 5 meters, what would be the final position of the car? So in this case right here, remember all we do is we take the final position is equal to our initial position plus our change in position. So we're going to take x of 15, which is our final time, equals x is 0 plus the definite integral of our velocity function from t equals 0 to t equals 15. Remember, this definite integral gives us our change in position. So that's going to be 5 meters minus 50 meters, since minus 50 meters is what we found for our change in position in the first part. So as a result, we get that the final position of our car is going to be negative 45 meters. Okay? And then lastly, if we ask what the distance did the car travel during this period, okay? Since the integrand for distance has an absolute value on the speed function, on the velocity function, this means that any negative areas we've calculated in the first part are subsequently going to become positive. So we're going to still have 1/2 5 times 10. We're still going to have 1/2 5 times 10 for a second triangle, and we're still going to have 5 times 10 for the first rectangle right here. Okay, but instead of having negatives for these second triangle and the first rectangle, we're now going to have positives, which when we do all the calculations is going to give us an overall distance of 100 meters traveled. So calculating averages now, okay? Our last part here, because I know we've covered a lot, okay? So to calculate average velocity or average acceleration over time interval, there are two ways that this can be attacked. One can be attacked from a perspective of average rate of change, and then the other can be attacked from the perspective of the average value of a function, building off of what we looked at in 6.1, okay? So let's take a look at these two different perspectives. So from the perspective of average rate of change, okay? So if we are provided a position function x of t and we're asked to calculate the average velocity, remember that average velocity can be calculated as the average rate of change of your position function. So we calculate the average value of our average rate of change of our position function. Likewise, if we are asked to calculate the average acceleration and we're given a velocity function, we can calculate the average acceleration by figuring out the average rate of change of our velocity function. Okay? Now on the flip side, if we are given, from the perspective of the average value of a function, okay, if we're trying to calculate the average velocity, but we don't have a position function, but velocity function, we can calculate the average velocity by using the average value equation from 6.2 for the velocity function, like we see happening right here. 1 over t2 minus t1 times the definite integral from t1 to t2 of your velocity function. And then likewise, if we're trying to calculate average acceleration, but we don't have a velocity function, we can use the equation for average value from 6.1 with the function for acceleration in order to calculate our average accelerations, which would be 1 over t2 minus t1 times the definite integral from t1 to t2 of our acceleration function. And this is the basics that we'll need in order to jump into higher level problems in class with integral calculus based motion.